Welcome back, my steel design friends. In today's lesson, we're going to be taking a look at Chapter D of the design specification. In the 15th edition, this will be on page 16.1-28, and we're going to basically be looking at tension member design. Okay, there are a couple of cases that we have to look at for tension members. Two of them will be strength and one will be serviceability, and we'll start kind of today with doing just kind of the basics of the different types of tension and how you know which case it is, and kind of some assumptions that we have to make along the way. In future videos, we'll get into some more advanced topics such as shear lag and serviceability requirements, but for now we're going to just kind of stick with the basics as we start to move through. So without further ado, let's get started. As kind of a quick overview of Chapter D, this is our first look at a specific section in the specification. Chapter D corresponds to tension because nothing spells tension like the letter D. I still have never quite figured out how they organized it, but I guess it works. It is pretty early on in the series, and so tension is generally one of the first topics it's covered because it's the most relatable to strength and materials, and so I think maybe that's just kind of the general flow of topics. But anyway, I digress. What we're going to look at is kind of how this typical section is laid out. Okay, and so for tension members, what you notice in the steel manual is that at the beginning of the page, if I kind of take my page and kind of turn it this way a little bit, you can see where my finger is set in here. These are what we call the white pages of the specifications. These will be the rules and the equations that you have to follow and adhere to. If you look back in the back a little bit, there's this gray section here. And in the gray section, there will be chapters that correspond to the chapters of the white section. And these sections are called the commentary. And they provide a lot more information on the background of why AISC chose to do certain things or why they made the assumptions that they did. So anytime especially in this series, if I reference to a section here in the white pages, it's expected, at least for my students, that you'll go read the corresponding section back in the gray pages to kind of get an understanding of what it is and why they're doing things. Now I'll try to spell out some of it, but to be honest, you have to read the specification on your own because I can't tell you everything. Okay, even as a practicing engineer, even if I see an equation, I have to go make sure I understand why they're doing what they're doing and is that an applicable practice for my certain situation, whatever it may be. All right, so it'll really make a difference in the next video when we do shear lag, but I just want you aware that there are two different pieces that are happening on that. So anyway, let's get back to our section here in the white pages, if you will. Okay, so we're looking at Chapter D. Okay, it's broken up into different sections. You can see that there's a slenderness limitation, and we'll explain slenderness when we get to serviceability here. Maybe not this video, but in the next video, that there's a maximum length that a tension member is allowed to have. Okay, in fact, its slenderness ratio is limited to L divided by R. Has to be less than or equal to 300 and we'll explain why that is and how you determine if your member is going to have that issue. Okay, the next one then is what we're after, is the section on tensile strength. Okay, and so all chapters are kind of laid out this way, that you have a chapter on strength and the relevant equations that apply to this. So for tension members, from looking at this, I can see that there are two forms of tension analysis that have to happen. One is here in A and the other one is in B. So in A, this is for what we call the tensile yielding in the gross section. This is commonly referred to as gross yielding. Okay, and in this series, I'll abbreviate that as GY. Anytime you see a GY, I'm going to be using these equations. And what that says is it says that the nominal capacity and tension is equal to Fy, remember that's the yield stress, multiplied by the gross area. Okay, so that's the nominal capacity, and if you remember from our LRFD definition, I also need a phi factor. The phi is equal to 0.9, okay? And you'll see that 0.9 pops up a lot whenever there's a yield case. Not always, but a lot of times if it's a yielding phenomenon, such as indicated by us using Fy here, then phi is going to be equal to 0.9 almost always. Okay, now again, there are exceptions, so make sure you look it up and get the right values, but for tension, that's absolutely the case. Okay, you can see that the ASD value is that 1.67 for the yield criteria that we talked about in the last video. Okay, but again, we're not going to do anything with ASD in this particular book, but they do give you both. The equation works for both methodologies, they just change the factors accordingly. Okay, the second case that we're going to look at then is tensile rupture in the net section. Okay, and this one is basically called the net fracture case, okay, and I'll abbreviate that as NF whenever we do our analysis. And you can see that this one is the nominal capacity PN is going to be FU times AE, and AE is an effective area. It's not the gross area, so we're going to have to do a calculation. Basically, a net section is a section that has a hole in it or a taper or something that reduces the gross area down for some reason. Okay, and we'll talk about some examples on that. So you have to do a different calculation on the area, and this leads us into a topic known as the effective net area, and it leads into shear lag and some requirements on that. But this is the basic equation. So the trick is, how do you calculate AE? And we'll cover that one in the next video. Okay, so we have the gross yielding phenomenon uses the gross area. This is the A that's tabulated in the front, and this chapter is up in the early section properties of the book. They always tabulate AG. It's just, how do I get from AG to an AE is the trick. Okay, so for net fracture then, phi is different. Again, it's a fracture case, and notice we aren't using Fy anymore, we're using Fu. So this is the ultimate stress of the material that I'm dealing with. And for this case, phi is limited to 0.75, because again, a yielding failure is generally more predictable and not quite so violent as a rupture failure. Or a rupture, if something breaks, you're done. Okay, yielding, things tend to deform, they stretch a little bit more, maybe you've got a little bit of reserve deformation before it comes crashing down. Okay, so that's why there's a difference in here, and this is a very good example of the effects of the load and resistance factor design methodology at play, is that they factor things differently based on the certainties of the phenomenon that you're looking at. Yield phenomenon, fracture phenomenon. Okay, so that's what I kind of wanted to point out to you, but all of that is located in this particular specification. And if you read through, there's some other sections as well. The net area, you can see, will show up here. We'll talk about that in the next video. And then you've got some other things more specific for built-up members, pin-connected members, and then some shear lag coefficients that we'll work on the next page. So for now, I'll set that aside, and we'll kind of keep on going with what it is that we're looking at trying to do. All right, so let me set that down. And we'll come in and kind of look at this idea. All right, so if we kind of look at tension members, the way that we know whether we're looking at a fracture or a yield phenomenon, okay, the nominal strength we said was divided into these two criteria. Again, this was the GY case, okay, and this was our net fracture case. They'll look something kind of like that. And for LRFD, the equation was that the ultimate load combination, applied load, had to be less than or equal to phi Rn, which was the design capacity of this. Again, Rn by itself is nominal capacity, phi Rn is design capacity. Okay, and so for tension, you'll see it written a lot of different ways. Sometimes they use a P, sometimes they use a T, but you'll notice this equation is exactly the same as the general LRFD equation. Okay, all right, so let's consider kind of a tension member that maybe it's a member that's being bolted to another member. And so I've got it kind of written or drawn out like this. So here's my tension member, and my load P is acting downward on there. Okay, the yield, the gross yield plane, then if you kind of think about this in 3 dimensions, and I'll kind of bring this down, you know, something like that, and then maybe, you know, if you have a hidden line back behind, you can kind of start to get kind of a sense of this thing in 3 dimensions. Then the yield plane is the plane that's right here. Okay, again, it's kind of into the page, if you will. Whereas the hole, the fracture plane is one that usually involves a hole or some reduction in the area. Okay, so whenever we design this member, there are a couple of things that are possible. I could yield out here, you know, or I could fail it at the connection. And you can't just assume that, oh, well, it's got a hole in it, it will always break here, because it doesn't. A lot of times what they do in highly loaded tension members is they provide thickened material up around the hole to help keep the stresses down, or to, you know, to keep things from it's not equal. Okay, and partially because you're using Fy versus Fu, and your phi factors are changing as well. And so it turns out that they're actually fairly close to each other numerically speaking. Okay, so we're going to look at the yield criteria of the way that this starts to look, okay, on the gross section, if you will. So this would be the width of the bar times the thickness of the plate if this were just a flat bar. Okay, the fracture location occurs on an area that is a reduced area from the gross. If this is the gross area, you can see clearly that if the smallest area corresponds to the center of the hole, and the hole is an opening, meaning there's no material, then I would have a region that's here, and then I would have a region that's here, that are all being subjected to the stress or to the load potentially. Okay, and there's actually more considerations to this than, when we get into shear lag, but in general, that's kind of what we're looking at. So typically, this is what we're going to consider both cases whenever we design a tension member for us there. All right. Okay. Now that brings to a question: how do we handle the holes? Okay. And so here's what we're going to look at. Okay. And so we have to kind of think about the creation of a hole as, as a physical process. Okay. Now, typically, most people may be familiar with making holes by taking a drill and plugging it in the wall and then drilling a hole through something. And that is one way, but in fabrication, that's a very time-consuming process. And so a lot of times when it comes to making holes, they do something like a punch. Okay, if you think about the old paper hole punch, the little apparatus, you put it in, squeeze the trigger, and then out pops the little ingot, if you will, paper ingot that makes the hole. You can kind of see a couple of them here. That's how I made these holes, right? Okay, well, that's a shear process versus a drilling process. And so how you create the holes is actually something we have to consider. Okay, and so there's a lot of different ways to make it. There is punching, which is the hole punch analogy, where I physically take, I have, 2 plates or even a plate, and I basically have a punch that's hooked to some press, and it's basically shoved down through there such that it pops out the material down below. Okay, that's a highly stressful process on this and can cause a lot of damage in the hole. Now, if I need a certain size of hole in order to be able to accommodate a bolt, okay, well, the punching process actually damages a region around the size of the hole. So I can't count on this region here for any strength. And it turns out that it's basically an oversize in the amount of 1/32 of an inch. Okay, or it's a 16th total on both sides. If you consider the diameter here, I've damaged the 32nd on this side and a 32nd on this side. That's a 16th total, okay, for extra damage that comes out of the process, okay? In addition, I also need to oversize the hole in order to be able to fit the bolt through. I can't have a hole that is 3/4 of an inch and expect to be able to put a 3/4 inch bolt in it. You have to have a little bit of room out beyond the size of the bolt, which is what we call the oversize. Okay, so if you kind of think about this in this way, here's my bolt. Okay, in order to get it in the hole, I have to add a little bit, okay, which would be what you're machining, and then I have to add a little bit more because of the damage that's created from the process. Okay, and so for us, whenever we do a punch process, which is what we defined here, we have to add a 16th of an inch, okay, extra. Okay, plus a 16th of an inch for the oversize. So that means that the size of the hole is going to be the diameter of the bolt plus 1/8 of an inch. Okay, now a lot of times on structural drawings, they don't specify the hole size. Okay, they specify the bolt. Okay, and then most engineers just by default will add the 1/8 no matter what, so that it leaves it free for the fabricator to decide, well, am I going to punch it? Am I going to drill it? Am I going to ream it? Any of the other methods. But punching is the most violent by far. And really kind of what happens is if this is my plate, whenever I punch it, if these are the inner holes that are happening, this guy you get kind of a sharp edge as this thing pushes down, because it's just literally I'm taking a piece of metal and shoving it through another piece of metal. Okay, and so that becomes kind of an issue, and it's this microfracturing that is the fracturing that we're talking about in this. Okay, so typically, and in most cases in this class, we're going to assume punched holes for everything. It's the most conservative, and we're going to take the diameter of the bolt and plus 1/8 of an inch, and that gets me, if you will, if I look at this picture here, this line, okay, it would be the diameter of what we count on as the hole, whereas if that's my bolt, then this guy is the diameter of the bolt, okay? And we use kind of a phi value to represent diameters on a lot of stuff. But on a structural drawing, we'll call out the bolt, okay? That it's a 3/4 inch bolt because that's what I need for strength. And then the fabricator knows, oh, well, I can add it, and I can do whatever I need to do. And in my design calcs, I typically add my diameter of the hole as being diameter of bolt plus 1/8 of an inch. Okay, and that's from pretty much every hole that we have to do that. So if you have multiple holes in a line and my fracture plane goes through multiple holes, well, then we have to correct that gross area to be able to come up with those particular values. So the way the holes are made is very important. So that's what punching is. Drilling is just you have a metal apparatus that's coming in here and it's spinning, and it's drilling, down through the paper like that. It's generally done with a magnetic drill of some sort. It's very time consuming, especially for very thick plates. For small plates might not be bad, but if you start getting into 1-inch plates or 1.5-inch plates, a good mag drill, it could take you 15 minutes to drill through that. Okay, so it's so that's a drilling, and then a reaming is kind of a combination of the two. I drill a hole, a small hole, and then I shove another piece inside that kind of reams it out and makes the hole wider. Okay, and that's generally a little kinder than a straight punch, but it's again, it's labor intensive because now you have to do 2 rounds of drilling, although they're probably a little faster than trying to do a big single hole drill on those. But those are the 3 methods that we talk about when it comes to drilling or creating holes in plates for connections. In practice, we like to use bolts because they provide for a faster construction technique. All the holes are pre-made in a shop usually. Okay, they may be plates that are welded on, tabs on beams, or at the end the tension members to connect to other pieces that are already out in the field. And then all that you have to do to erect it is pick the piece up and then place it and put the bolts in, and you're done. Okay, whereas if you're welding, then you've got to have a way to hold the piece in place. There's got to be a certified welder on site and those kind of things. So bolted holes are a lot more labor up front, but generally the construction of the structure itself occurs a whole lot faster. And that's one of the reasons that we like these drilled holes. And I can drill these holes in a shop environment where there's some quality control, and I can guarantee that things are more likely to be the way that I expect them than if I try to do something in the field. Okay, so that's kind of the nature of what's going on with the holes. All right, now let's talk a little bit conceptually about stresses as we start to kind of look at what stresses are doing at the holes. Let's suppose that I have a bar in which I'm pulling on both sides. On both ways. And you may have covered some of this, when you're looking at stress concentrations back in your strength and materials classes. But what happens is that if I have my load, we always draw the load as a singular value, but in reality, what we're looking at is some sort of load that's spread out over the length of the member, like this, and then how are these stresses starting to kind of move from one side to the other? And so if we have a hole in the middle, if it's a straight piece without a hole, these lines just go straight across and it's not a problem. But if I start putting a hole, what happens is these guys have to start kind of funneling around the hole. And if you think about each one of these arrows is a certain amount of stress, if you will, this is kind of a stress flow diagram that looks something kind of like that, that now I have load for a half of a member that's getting funneled over to here. Okay, and it's wrapping around, and it's going as close to the hole as it can, and that's why we get actually a spike in the stress at the edge of the hole. Those are those stress concentrations. Same thing happens if I have, some sort of coped corner as well, right? That, if this is where my tension is being applied and this is where the other end of it is, this guy's kind of trying to flare out. And you can see that now I get a concentration that's kind of at the edge of this cope, depending on the shape of the cope, whether it's a square corner around it. It's the same basic idea. Okay, now, so what that means is that I can have an F max that's very, very high here, but maybe out here is a stress value that's significantly less. Well, if I'm being ultra conservative, I should be designing for F max. But if you look at that, I'm over-designing for locations at the edges of the holes when the rest of the member isn't seeing anything near that amount. Okay, and in fact, studies have shown that the stress at a round hole can be almost as much as 3 times what the average stress is. Okay, meaning that the average value of this guy is the maximum can be up to 3 times as much. And if I'm limiting myself to this as my capacity, I'm going to have a very inefficient design section. But if I'm willing to live with a little bit of deformation at the hole, I can get some significant savings by now, instead of using that maximum value, using an average value, okay, which is the way that LRFD and AISC are going to approach the problem. That now this is, if I call this as my F max, which is actually an F average on there, that now instead of assuming this peaked true max stress value, I'm going to take an average stress instead, and that will be my max stress. And now it's the same everywhere. So what you've done is you've come across here, and I've underestimated this portion and overestimated this, but at the end the average is about even. Okay, and so what we're going to assume in AISC is we're going to assume that the ultimate stress is ultimately uniformly distributed over the section. Okay, But because I make this assumption, now I've got to correct for this funneling effect that we were talking about with these flow diagrams. And that will lead us to a concept known as shear lag, which we'll get into in our next video. Okay, so if we kind of take a look at this, there are some rules for how you calculate the effect or the amount of the shear lag effect or the concentration that's occurring. Okay, so let's go back and kind of go back to our two cases that we had. Okay, so here's my gross yielding again. Okay, that was Pn is equal to Fy times Ag. Ag is the gross area, Fy is the yield strength. And then the fracture of the net section, which was my NF case, okay, was Fu times Ae. Now, for bars, the actual equation for Ae is called the effective area, and it's actually equal to a parameter U called the shear lag coefficient multiplied by the net area. Okay, and the net area is basically the gross area minus any subtractions due to holes or loss of material. Okay, and so for us, what we're going to assume in our case is that U is going to be 1.0, which for most flat plates, that's generally a safe assumption. Okay, and then AN is just gross minus, so this is our net area. And if I want to write this down, we're going to say that this is A gross minus A holes. Okay, and then we're going to use the ultimate stress, this FU value for the material that we're working on. Okay, so the question in all tension design then is how do we calculate the areas? Okay, so let's take a look at kind of a simple example. We're going to assume A36 steel, which means we know from our material properties, A36 is one of the standards. Okay, that Fy is 36 and Fu is 58. Okay, I'm going to put a 3/4 inch diameter standard hole. Okay, and the standard hole, these are the holes that I was just talking about. Okay, and the standard is important because that tells me that we've added a 1/16 for the oversize. Okay, it is possible to have an oversized hole for, you know, special circumstances, in which case you've got to be real careful that you add in the effect of the oversize. Okay, but again, everything we're doing here is a standard hole. An oversized hole could be as much as 1/8 by itself. Okay, or you could get into slotted holes in which it could be significantly more. Okay, but for us, we're going to do the standard hole. So you'll see the standard hole idea very commonly. Okay, we're going to assume it's a 3/4 inch diameter, so that's the bolt size. And generally there would be a specification that says, oh, this is an A325, you know, X or an N or something that will have some meaning when we get to our bolt strength calculations later on, but that would be kind of the labeling that would happen. Okay, the other piece of information we have is this PL. It's kind of this P overlap L, or sometimes you'll just see it written as a normal PL. I've always just written it as an overlap. Okay, and then it's a 1/4, which that's the thickness of the plate, by 4, which would be the width. So this plate is 4 inches wide and it's a 1/4 inch thick. Okay. Okay, and so when we look at what we're doing here, okay, is that the standard hole, as we said, was a little bit of an oversize that we're going to add an 1/16 on either side. So an 1/8 inch total to each diameter, and that will kind of get us, it's a little bit larger than just the minimum amount that we add in. Okay, so if we kind of look at this, so we're going to look at, well, what's the gross yielding capacity and what's the net fracture capacity? Okay, and so that will be our example that we're going to look at. All right. Okay, so what we're going to look at, we're going to look at the gross area. So again, we had a bar that was looking like, you know, they had a cross section where this was a 1/4 and this was 4 inches, and that's the cross-sectional area of the bar where the load is, the internal stress is acting. Okay, and so my gross area then is just 1/4 by 4. It's this shaded region right here that we're looking at. All right, so the gross area is 1/4 of an inch times 4 inches, 1 inch squared. Okay, the net area then, with the hole in it, we had a little bit of an area up above the hole, and then we had a gap, and then we had a little bit of an area below the hole. Okay, the width is still 1/4 of an inch there, but now we've got to figure out what's this guy called, which is the difference from here to here, because we know the whole thing from here to here is 4 inches. This ends up being whatever we compute for the diameter of the hole. Okay? All right, so if we look at what we're doing for our standard hole in here, we're going to do AN is going to be 4 inches total width, okay, minus, okay, let's add, we're going to label this is our thickness over here. That if I take 4 inches and I subtract off the diameter of the hole, that would be this area plus this area. Whoops, sorry. It would be this area plus, or this length and this length added together. So this plus this should be equal to 4 inches. So all I'm doing is I'm rearranging a little bit and going, okay, well, this is 4 inches minus the diameter of the hole, okay, is going to be 3/4 of an inch. That was the bolt, plus a 1/16 for damage, plus a 1/16 for the standard oversize. So this is that plus 1/8 term that we have. Now, like I say, in most of my calculations, I tend to write both just so that I can remember that I did consider both, okay, so that I know where the 1/16ths are coming from. So that's going to be 3/4 of an inch plus 1/8 of an inch is 7/8 of an inch. And I'm going to take 4 inches minus that number, and then I'm going to multiply. So now I've got my true width, this length plus this length, and all I have to do to get the area is now multiply by the quarter. And if I do that, the area is 0.78 inches squared. Now, you may be inclined to look at this and go, oh, well, the gross area is larger than the net, the smaller area should control. And this is where we say not so fast. Because again, remember, this guy in the net fracture calc is going to use FU and phi of 0.75, whereas this guy is going to use Fy and a phi of 0.9. So which of these products is smaller is the one that's going to control. So let's take a look and give it a try. Okay, so if we kind of take a look at this, okay, the limit states that we said are for yielding, the gross yielding case, this is GY, okay, Pn is going to equal to Fy times Ag, which is going to be 36 KSI, that's the Fy value, multiplied by Ag, which we computed to be 1 inch squared up here. And if I do that, then the nominal strength in gross yielding is 36 kips. Okay, for fracture, we know that Pn is equal to Fu times Ae. What is Ae? Okay, now, for a lot of factors, and again, there's a whole lot of criteria for plates that will come out. We'll talk more about where these are coming from on there, and it has to do with the length of the plate is more than 2 times the width, and a bunch of other factors. U starts to change, okay? But for a single bolt, we're going to take U as 1.0 anyway, and AE is going to be equal to AN, okay? And by single bolts, we mean the number of bolts that are in a line, down the length of the member. Again, we'll talk more about this. Just for now, let's just trust that U is 1.0, and I'll show you where these factors come from in the next video when we do shear lag. Okay, so then if that's the case, for us, for our net fracture, our effective area we said was going to be equal to U times AN. So that's why if U is 1.0 here, then AE is AN for this problem. Then my nominal capacity is going to be FU. That guy is FU, and this guy is my AE, which was my UAN for a single bolt. Okay, and so if I do that, then the math on this is 45.2 kips. Okay, now, again, yielding less than fracture, right? We had 36 kips for yielding up here, and now I have 45.2. Clearly, this guy controls. Well, again, remember, we have to put the phi factors on. You can only compare design strength, not nominals. So if I take my phi Pn, and now I put my phi on there, 0.9 times its Pn of 36 is 32.4 kips. Okay, phi Pn of 0.75 multiplied by my Pn of 45.2 kips gets me 33.9. It was a lot closer than we thought it was. And in some cases, especially if you have lots of bolts in a line along the same failure plane, this number can dip below the yielding value. Okay, so you have to check this for phi Pn every single time. Okay, you've got to check the capacity with the phi factor on it. Okay, and this will be a common type of test question or quiz question for those of you that are sitting in my class. Got to remember phi, never forget phi. Okay, all right, so our phi Pn capacity for this is now 32.4 kips. Okay, so that would be the design capacity. Well, what if we want to know, well, what's the rated load that I can put on this thing? Okay, so if, say that we knew that the load was 60% dead load and 40% live load, can you tell me what the maximum P value that I could put on this in terms of the service factors? And the way that you do that is here. So here's my factored load. Here's my equation, 1.2 dead plus 1.6 live, just like we talked about. That's our load combo. Okay, and so then the maximum load or the load rating on this would be 1.2 times 60% of P max. That's the 60% because we said that was the dead load, and this is the dead load factor. Plus 1.6 times 40% or 0.4 times P max is the live load factor. And if I do this math, then this whole thing equals 1.36 P max. Okay, so basically the factor of safety on this is going to be 1.36. Okay, all right, and so I can then solve for P max. We can say that P max then, because at the worst case, we say PU is, it should be less than or equal to phi pn. Okay, the absolute maximum value this guy can be is the equal case. All right, so we can bring in phi pn, which we saw as 32.4 kips. And if I rearrange this equation, then I do 32.4 kips over 1.36. The load rating that you would put on a sign beside this member would be, don't put more than 23.8 kips on this guy. And if you do that, then you'll be safe for yielding, you'll be safe for fracture, and you will have met all of the load and resistance factor requirements in doing so. So anyway, that's kind of the basics for how this methodology starts to work. We did gloss over a lot with regard to the net fracture or this effective area, and I'll show you that in the next video on how to do that. So anyway, I hope this has made sense to you. Again, remember your holes. Remember to add your oversize. Is it a standard hole? Is it an oversized hole? Is it a slotted hole? Make sure that you add the 16th for damage. Typically, we just add that, to cover the case where it's punched. If it's drilled, well then the connection's stronger than what you're expecting to be. It's just conservative to assume that it's always punched. Okay, and for this class, I'm cool with that as well, unless I specify otherwise. Okay, but those are all kind of some basics into designing tension members. Okay, again, there are some other things we have to consider, and we'll do that in the next video. So as always, leave us some connections, some videos, leave us some comments down below if you got any questions, and as always, be sure to like and subscribe to the video, and we will see you guys next time. Have a great evening. Happy engineering.